Hello friends. Today, I think in the last lecture we stopped at CPU. We are going to start where we left off. I hope you can see my screen now. Um, in the last lecture we were talking about CPU and how CPUs are evolved and how their capacity is increased, how their performance is increased, and how their size is increased these days. Um So this is these are main components of your CPU. So your CPU has registers, arithmetic logic unit. It also has an internal bus, and it also has a control unit. And we can call this control unit as brain of your computer. And again, this is the structure of your control unit. Uh, so here we have sequencing logic, control unit registers and decoders, and control memory. We'll study these components and their structures in detail in later chapters. Uh, but right now, let's just discuss a brief history of computers. So, when were the computers, how the computers started, how it was invented? Let's start with that. So, first computer was ENIAC, Electronic Numerical Integrator and Computer. And after that came EDVAC, Electronic Discrete Variable Computer, and this is also called as von uh, Neumann architecture. This architecture this computer has is called as von Neumann architecture. And next computer was IAS computer. So let's see what is the structure of IAS computer. As you can see here, we have a main memory. Then we also have a arithmetic logic unit. We have a program control unit and input output equipment. So this input output equipment will be used to input data. Then arithmetic logic unit will process that data, and that will be stored in your main memory. And whenever you want some result back, then you have to go to your the program control unit will go to main memory and fetch that result, and it will send that result to your output device. Let's take an example, a simple example. Let's say if I want to add two numbers, so you will give these two numbers through your keyboard is an input device. Then that will be uh, first fed to your program control unit. Okay, then program control unit decodes the instructions, what should be done. It will decode what should be done, and then it will send those instructions to your arithmetic logic unit, and arithmetic logic unit will send the result after calculating to your program control unit. Then again, program control unit will check whether the result needs to be saved or not. If it needs to be saved, then it will send the result to main memory. Otherwise, it will directly send the result to your output devices. Okay, I hope that's clear. So this is the main structure of IAS computer. This is not how our computers look like today. It's very complicated nowadays. So we can say that our the computers we are using today, their structure is based on this IAS computer structure. Now, let's see detailed structure of your IAS computer. See here, you can see you have arithmetic logic unit. This is your program control unit. This is your main memory and this is your input output equipment. Now let's continue with the same example. I told you I have sent two numbers for addition. Now I have taken these two numbers, okay, from your input device. Then see how they travel. They are first going into this register. Okay, this is memory buffer register. So this register stores, this memory buffer register stores whatever data you get from your input devices or whatever data you want to send to output devices. Okay, so it works in both ways. So I have gotten data and I have saved it in this MBR. So my first number is now saved in MBR. Uh, then it will go to this program control unit. Okay, uh, sorry. See, when we are trying to add two numbers, our main purpose is to send the instructions to your computer in that way. So you will have to send instruction and also data. So when you are the instructions will be sent here and the data will be sent here. Okay, so my first instruction, it will come here in instruction buffer register. Then that instruction is stored in see, again instruction has two parts, the instruction part and data part. So instruction part will be stored in this instruction register and data part will be stored in the address of the data will be stored in memory address register. Then this instruction is decoded by these control circuits and control signals are sent. Okay, these control signals are sent to your arithmetic logic unit, and here actually the addition happens. So if you want to add two numbers, first number is copied into your accumulator, then next number will come, then according to the control signals this second number will be added to your accumulator, and again contents of accumulator will be replaced by the addition. So you won't have the numbers you have already sent for addition. So your accumulator now will only have the addition of your two numbers. Okay, the addition part actually happens with these arithmetic logic circuits, and this result what accumulator has, it will be sent to uh, again your program control unit. Okay, and then it will be decided where to send the result. If you want to save the result, it will be sent to your memory, otherwise it will be sent to your output device. Okay, so that was with an example. I hope you have understood the structure of IAS computer and how your IAS computer works. Sorry, I forgot to tell you these two registers. This is program counter register and this is memory address register. So this program counter register increments every time after execution of an instruction, and it stores address of your next instruction, and we are assuming that all the instructions are stored in sequential locations, so it will just increment and you will have your next instruction. And when you have the instruction, it will be first copied in this IS computer fetches two instructions at a time. That's why one instruction will be stored in instruction buffer register, and the second one will be taken for processing, and its instruction part will be stored in instruction register, and the address part will be stored in memory address register. And from this address you can get the data from your main memory. Okay, I hope that's clear. Now let's see what kind of instructions are there. There are data transfer instructions. There is unconditional branch. There is conditional branch. Next is arithmetic instructions, and last one is address modify instructions. So first instruction is data transfer instructions. So data transfer instructions are like moving your data from one location to another location. That is your data transfer. Or copying data from one location to another location. Next instruction is unconditional branch. So unconditional branch means so it will be something like your go-to statements. So you are jumping to another another instruction in your program, and not in sequential way according to your condition. So that is unconditional branch. And in conditional branch you have to check some kind of condition, like if one number is greater than the other number, then you are going to perform you are going to execute a set of instruction, and if that condition is false, then you are going to execute set of another instructions. That is called as conditional branch instructions. And so if else, if only if, these kind of instructions come under this category. Next are arithmetic instructions. So add, subtract, divide, multiply, or these kind of instructions will come under this category, arithmetic category. The next instructions are address modify instructions. So in this case, you are trying to change the address of your data, and these instructions will come under this address modify instruction category. Now, up until now, we have discussed about IAS computer and EDVAC computer and ENIAC computer. ENIAC computer and EDVAC computer, they were first generation computers. I hope you know that in first generation computers, vacuum tubes were used. And in second generation, now let's discuss about second generation computers. In second generation computers, transistors were used. A transistor is a solid state device. It is made from silicon. And in second generation, more complex arithmetic and logic units and control units were introduced. And from second generation, high level programming language, use of high level programming language was continued. And provision of system software with the computer. So nowadays your computer comes with an operating system. So that started from the second generation computers. Some kind of system software. So here you can see this is an IBM 7094 configuration. See, it has a CPU, a multiplexer, memory, and data channels. Here you can see other components: magnetic tape units, card punch, line printer, card reader, drum, disk, hyper tapes, and teleprocessing equipment. And after second generation computers, third generation computers were introduced. In third generation computers, integrated circuits were used. Data storage was provided by memory cells and processing was provided by gates. So here you can see the structure of a gate and a memory cell. And remember, when I'm talking about data storage and data processing, so data storage in a cell is kind of saving in only bytes. So the one cell will contain either 0 or 1. And this cell has again input, output, and read and write signals. And I hope you remember the gates: AND gate, NOT gate, NAND gate, XOR gate. By using these gates, data processing was done in third generation computers. Here you can see the graph of growth in CPU transistor count. See, in second generation computers, transistors were used, and as the time goes by, the number of transistors is increasing. You can see here transistors per chip, and these many transistors can be fitted on one integrated circuit chip. Okay, so up until 2010, you have about 10. It has reached up to 10 raised to 9 transistors per chip. Now let's talk about IBM System 360. This IBM system was created so that it will have uh, it is like a family of computers. So some configurations were different, but the overall operating system was same and the instruction set was identical. So the only different parts would be the size of your memory and the speed with which the computer processes the data. That would be different. So this is like a family of computers, IBM 360. And as the time goes by, the speed of the processors was increased, the number of IO ports were increased, memory size was also increased, and cost was also increased. Then after that, microprocessor was born. Uh, See, when I'm talking about microprocessor, all the components of a CPU will lie on single chip. That's why it is called as a microprocessor. See, 4004 was the first chip to contain all the components of a CPU on a single chip. Uh, See, Intel 8008 was the first 8-bit microprocessor, and it was invented in 1972. And 80386 is 32-bit microprocessor. Now, our next point is designing for performance. See, when we are talking about a computer, what is important is the performance of your computer, not the speed of your computer, but performance. And remember, these are two different things. And uh, applications in which you are currently using your desktop are, your computers are, image processing, speech recognition, video conferencing, multimedia authoring, voice and video annotation of files, simulation modeling. So uh, right now you are using uh, your computer for these kind of applications, and for that your computer needs to perform, uh, your computer should give very high performance. That is important. So how we can improve the performance of your computer? For that we have different techniques. Um, of course, the performance depends upon the speed of your microprocessor. And let's see how we can increase the speed of your microprocessor by using few techniques. So first technique is branch prediction. So microprocessor will predict which branch will be executed next, and that set of instructions will be previously loaded in your CPU, so that uh, when so that the speed will be increased. The speed of execution of instructions will be increased. Next technique is data flow analysis. So in this part, you can study the history of data, how the data flows, and based on that, the microprocessor or your CPU can take decisions about data, which data should be fetched, which block of data should be fetched. Next one is speculative execution. So this is again uh, based upon prediction. Speculative execution means um, if you have some instruction, you will be actually predicting which instruction will be executed next. That is called as speculative execution. See, in this graph, you can see logic and memory performance gap. See, graph of logic is pretty steep, but graph of memory is not that much increasing. It's about a flat curve. See, these are a few more techniques to increase the speed of your computer. First one is increase the number of bits that are retrieved at one time by making DRAMs wider. DRAM is dynamic RAM. A cache 7 or other buffering scheme on DRAM chip. Reduce the frequency of memory access by incorporating increasingly complex and efficient cache structures between the processor and main memory. Next one is increase the interconnect bandwidth between processors and memory by using high-speed buses and by using a hierarchy of buses to buffer and structure data flow. In this graph, you can see the I/O devices and their data rates. Improvements in organization and architecture. Even though you have increased the speed of your processor, it not necessarily improves the performance. So for improving the performance, organization is very necessary. So all you can increase the hardware speed of processor. So for improvement in your computer performance, you need to increase the size and speed of caches. Also, you need to make changes to the processor organization and architecture. The issues will be your power, RC delay, and memory latency. Memory latency means the time it takes to copy data from your memory to your CPU and vice versa. Here you can see the graph of Intel microprocessor performance. As the time goes by, the performance is increasing. Here you can see the evolution of the Intel x86 architecture. So it started with 8080. It is an 8-bit machine with 8-bit data path to memory. In 8086, you have 16-bit machine with a wider data path and larger registers. 80286 is enabled addressing a 16 megabyte. Then landmark is your Pentium processor. So Pentium processor has superscalar techniques which allow multiple instructions to be executed in parallel. And again, in Pentium also there were few improvements. So here you can see all the improvements in Pentium processor. And first, and then came the core processors. So these core processors will have a dual core. So at the same time, you can say that you have two CPUs at the same time. See, core 2 quad provides 4 processors on a single chip. So when you are buying anything with octa core or quad core, it means you have that many processors, so that your device's speed is increased and performance is increased. Now let's talk about embedded systems. Embedded systems also use softwares. Combination of computer hardware and software and additional mechanical or other parts designed to perform a dedicated function is called as an embedded system. In many cases, embedded systems are part of a larger system or product. Examples are kitchen appliances, automotive machines, in medical field, or in industrial control, or in office automation. You can also use embedded systems. Next point is ARM evolution. I think we should stop now. We'll discuss this remaining part in our next lecture.